A 0.6 volt, 0.65 milliwatt RF front end for Bluetooth Low Energy in CMOS 90 nanometer technology. Hello everyone, we are Denshen,品蓁, and Yuchen. Our instructor is Professor Guangwei Chen. This video will first talk about the basic introduction to the RF front end. And then we'll discuss the three main block circuits in this RF system, which includes the low noise amplifier, LNA, mixer, and voltage-controlled oscillator, VCO. At last, we'll show the simulation results and compare the performance with other IEEE conference and journal papers. RF front end is gaining demand in many applications ranging from remote sensing, healthcare monitoring, wireless communication, and security system. The main challenge of these systems is ultra-low power capabilities to allow several months or years of operation using a single lithium-ion battery. In this project, we use several circuit techniques to design a RF front end that has good performance under an ultra-low power operation. A RF front end is used in receiving the signal from the air and down-convert the high carrier frequency signal to intermediate frequency level. In this system, LNA is responsible for amplifying the high frequency signal from the antenna and is focused on noise, linearity, and gain. VCO provides a local sine wave and is focused on the phase noise. Mixer is responsible for frequency mixing and is focused on linearity, noise, and gain. This is the proposed circuit of our LNA. We stack a PMOS on top of the NMOS that the two transistors can share the same bias current. As a result, the overall transconductance will be the summation of the transconductance from NMOS and PMOS. Namely, we can almost reduce 50% power dissipation from this topology. Also, we introduce a trifilar transformer consisting of a primary coil and two secondary coils. Enhancing the coupling factor and saving the area are two advantages of trifilar transformer. We design and implement our own trifilar transformer and inversely coupled the gate and the source of the NMOS and PMOS transistors. By doing so, the transconductance will be enhanced to 1 + T times without extra power consumption. Therefore, we can save the power 1 + T times smaller than the original one. Current efficiency is widely used in analog circuit design, whose the operating frequency is far from the transit frequency. However, the transit frequency plays a key role in the field of RF due to the effect of parasitic, such as gate and source capacitance. To decide the bias condition, we multiply these two figures to find the sweet point of each transistor in this work. We use a Smith chart to construct a matching circuit that guarantee the input impedance of the LNA will be equal to the impedance of transmission line, which is generally 50 ohms. Due to the above techniques, the proposed LNA achieves ultra-low power, low noise, high gain, and high linearity. The performance of our LNA is characterized by the conventional figure of merit FOM for LNAs. This table shows the comparison of the LNAs in our work and other papers. From the figure of merit FOM, we can find that our LNA seems to be better than other IEEE conference and journal papers. This is the proposed circuit of our mixer. The main function of the mixer is the multiplication of two input signals from LNA and VCO, which is 2.4 GHz and 2.5 GHz in this work. A low-pass filter is utilized to select the signal in our desired band, which is 100 MHz in this project. A traditional passive mixer performs well on power and noise due to the absence of the drain current. Meanwhile, the linearity is also the advantage of the passive mixer. However, a negative conversion gain is fatal for the passive mixer. To solve this problem, we introduce a transimpedance amplifier, TIA, which amplifies the signal in the baseband. The TIA is a fully differential amplifier consisting of a pair of inverter-based amplifiers that operate in subthreshold region for ultra-low power applications. Due to the property of fully differential, the TIA needs a common mode feedback circuit that drives the correct output voltage level. Due to the above techniques, the proposed mixer achieves ultra-low power, low noise, high gain, and high linearity. The performance of our mixer is characterized by the conventional figure of merit FOM for mixers. This table shows the comparison of the mixers in our work and other papers. From the figure of merit, we can find that our mixer seems to be better than other IEEE conference and journal papers.
Okay, and now it's my turn to talk about the voltage control oscillator, VCO. In this project, all of the circuits are operated under 0.6 volt supply voltage. To have large output swing within this low voltage supply is the challenge we need to deal with. This proposed transformer feedback VCO with first, field swings, second, inductor source, and third, second tank are the solutions due to this issue. We use a pair of coupled inductor LD and LS to get an output swing higher than VDD or lower than GND. Second, to get an extra headroom for the output swing, we use an inductor source instead of the traditional transistor bias. Third, also, we add a capacitor for the second tank at the source drain and make it resonate at twice the output frequency so that we can reduce the flicker noise out conversion. Through these techniques, we can obtain a low power consumption VCO but still with an outstanding phase noise. In this chart, we can see that we have better performances in almost every characteristics. The total FOM is a lot better compared to other papers in some famous conferences. And here comes the comparisons and the conclusions. Here are our transient results of all blocks. This is the output of the LNA and VCO respectively, which are 2.4 GHz and 2.5 GHz sine wave. And this is the IF output after mix. And at last, we can get a clean sine wave of 100 MHz after the low-pass filter. The total power consumption is 0.65 mW, with VCO consuming the most power. As we can see by the table, we have competitive performance amongst all of the references, especially in power. The power of our circuit is the lowest in the state of art. In conclusion, we integrated three important blocks into a complete RF front end. And we did achieve the goal we've set, an ultra-low power system with good performance. Meanwhile, we submitted the proposed LNA to RFIT conference and taped out at TSMC 19nm technology. Also, the PCB is designed for a measurement. By the way, we will continue to improve the topology of VCO and looking forward to tape out the Fuji. And this is the end of our video. Thank you for your attention.